This is going to be lesson 4.9. I'll make it as brief and quick as possible. Whenever we come to a slide that has a question, I'll pause for a moment for you to pause the video, guys, because I am going to go right into answering the question. I'll give you 1 to 2 seconds to pause the video right now. Okay. So inertia, if you recall from 4.2, right, it was part of Newton's first law of motion. Inertia is proportional to mass. So the more mass you have, the more inertia you have. But what is inertia in the first place, right? Inertia is essentially the inherent property of an object to really continue its motion, right? It doesn't want to change its current motion unless acted on by unbalanced force. If you take a look at the bottom right hand GIF right here, right, you see the skateboarder, his skateboard stops because it runs into the hose, but there's nothing stopping the person. So the person keeps going because, well, because of inertia. They want to keep going unless there's an unbalanced force acting on them, right? They want to keep going. They refuse to change their current motion. But now we get into something called momentum, right? Because momentum is essentially a description of both. Rather, momentum is the property of an object that has both mass and velocity. So momentum is given by the formula P is equal to m times v, right? And so P is going to be your momentum, and the unit for that is kg times meters per second, which makes sense because in the formula, m is your mass measured by kg, and v is your velocity measured by meters per second. And so, well, the formula for momentum would just be kg times meters per second. So you have more momentum if you have a higher velocity, you have more momentum if you have a higher mass, etc., etc. Now, momentum is a vector quantity. Direction is important, right? You either go to the right or to the left, up, down, it doesn't matter. Momentum has a direction. So let's get into the first practice problem, right? So let's get into this. Now, so you analyze the problem, 5 kilograms. Again, you should pause it right now if you kind of want to do it yourself, right? You want to attempt it yourself, so just pause the video. Because right now I'm just going to solve it. So your mass is 5 kg. You slide along the surface at 10 meters per second. It is a frictionless surface, so you don't have to worry about anything else. Your time is 4 seconds. And they want to know, well, what is the magnitude of the block's momentum? Well, the formula for momentum, right, is 5 kg times, well, it's 5 kg times 10 meters per second. And then, well, you get 50 kg times meters per second. And that is the answer. Feel free to pause it if you would like to do so. And so here on the Google Slides, I do give you the answer, right? I kind of highlight all my work. So if you kind of want to go back into the Google Slides to see what the answer is, feel free to just go back. Now we're now going to go into the second practice problem. Now this problem is a little bit more difficult. Right? They're telling you, again, pause the video if you kind of want to attempt the question yourself first. So you're given a 0.06 kilogram ball, right? So you can say that what the mass is 0.0600 kg. And it's traveling at 60 meters per second. So let's just say that, right? And what speed must this bullet have? What speed must a 0.0100 kilogram bullet have in order to hit the wall with the same magnitude of momentum as the ball? So now this is a two-step problem because now we have two masses, right? So what I can do here is going to say v m sub 1, v sub 1. my v sub 2. And then I have a second mass, right? And so, well, my second mass is that. And they want to know, well, what is the speed of the second mass, right? If they were to hit the wall with the same magnitude of momentum. So we know that, well, the momentum of object 1 should equal to the momentum of object 2. But we also know that due to the formula, right, momentum is equal to mass times velocity. Well, we can just break it down like that, right? We can just do this instead. And now all we need to do is substitute, right? And that gets you 0.0100 kg. And that gets you v sub 2. And then you just do some math here, math manipulation. And then you solve for v sub 2. I'm going to leave that to you. All right. That's not really something I want to do. All right. Yeah. As depicted here, right? And again, the answer, the work is on Google Slides as well. So again, I'm going to give you guys time to read this, right? But I am going to describe this question. So here you see two gifts, right? So someone's throwing an egg at a wooden board, and someone's throwing an egg at a bed sheet. And clearly, one of these scenarios, the egg breaks. Now, but then why, right? And now a lot of you guys are saying, are probably going to say, well, because the wooden board is hard. Right, and the bed sheet is soft, and so that's why the egg doesn't break. But let's try and explain this using actual physics, right? Now let's think about it. Both eggs reach a momentum of 0. Right, both eggs reach a momentum of 0 when they hit the object, right? Because they all stop. Because we know that, well, the velocity they reach is 0 because they stop, and so thus their momentum is 0 at the end. Let's say, well, it's their final momentum because we initially threw it with an initial momentum that was greater than 0. And so my final momentum of the egg is 0, and so my change in momentum, delta P, would be the same, right? It's the same in both situations. But if you take a look at the graphs on the bottom, you'll see that the applied force that occurs in both situations is clearly different. Because when you throw the egg at the wall applies a force on the egg really at a singular point in time, like really over a brief moment in time. Whereas the sheet applies a force on the egg over a longer period of time, and because it applies a force over a longer period of time, there isn't as high of a peak of force. And so because there isn't as high of a peak, because it took longer for the egg to come to a stop, that force was spread out. And because the force was spread out, there was never a moment in time where the egg experienced a large enough force to really break the egg. And this is a concept of something we call impulse. Now, before we get into impulse, let's analyze this situation, right? So let's take a look at this formula. You're going to see this formula on your reference table. Your net force applied over a period of time is equal to the change in momentum of the object. So to change the momentum of the object, you need to apply a force over time. But and now this change of momentum part right here, I want to talk about it. This change of momentum part, again, change of momentum is just the final minus initial. That's essentially what change is, right? So change is your final minus initial. You might have seen this before, right? Change in y is essentially your final y minus initial y, or as you guys are used to, it's your second y minus your first y, really. Really, that's just what delta means. Delta is your final minus initial. And if we were to put delta p here, right, well, that would be my final velocity minus my initial velocity. And if we further break it down, right, we know that my final momentum is equal to mass times my final velocity minus my mass times initial velocity. But because again, what we can do is we can factor out the mass. And because we're factoring out the mass, now we have mass times final velocity minus initial velocity. But we can substitute that part as m delta v, because again, delta means final minus initial. So we can come to that identity there. And so I break down the formula as shown in the slide. Let's take a look at this formula again. Really, now that you see the errors, and let's compare a situation in a car. Cars are designed for your safety, right? For example, airbags. Airbags are a really good example of this formula, because what an airbag does is it increases the time for you to come to a stop. And because it increases the time, it extends the time of collision. If you look at the formula on top right, because you extend the time of collision, you decrease the amount of force that you experience, or rather your average force that you experience over a certain period of time. And so let me put it to you guys this way, right? So let's say in one situation you have no airbag, right? So no airbag. And in the other situation, you do have an airbag. And so let's say your time here, and we're going to put in 0.1 seconds because the car crash just happened in that amount of time frame. And so let's do this. And so let's say the airbag, and this is not really what happens in real life. Your force does vary. I'm really just simplifying it for Regents physics. And so let's say the airbag applies a force of 200 newtons, really just spread out over this time interval. So each of these intervals, you have an applied force of 200 newtons on you. I'm sorry, this should be on the airbag side. And so on the airbag side, the airbag helps slow you down, increases the amount of time it takes for you to come to a stop, so you don't experience brain damage, or really less brain damage. But in the no airbag scenario, you come to a stop almost instantly because you just hit the steering wheel. And so let's say you experience all that force literally in just 0.01 seconds. Right? So now you're not, all this force is experienced in essentially 0.01 seconds, whereas with the airbag, you experience a force spread out over time. And so in the force that's spread out over time, well, you don't experience as much damage. There are also other ways that cars are designed using this principle, right? For example, the crumple zone, you see the hood of the car. When you crash head on, the hood crumples, right? The car crumples, and so does the bumper, by the way. But this crumple zone, this effect, what it's doing is that it further increases the time it takes for the car to come to a stop, thereby ensuring even more greatly ensuring your safety. So this is really important. Now, this is again to cause a change in momentum, you need a force applied over time, right? So to change an object's momentum, you need a force applied over a period of time. And that's also just nicknamed something we call impulse. Impulse's literal definition is change in momentum of an object over time, after a net force is applied over a period of time. That's literally what impulse is. Impulse is represented by the letter J. So you'll see this entire formula on your reference table. If you want to take some time to analyze it, you can. Impulse is also a vector quantity. And you guys can also watch this video on your own time. All right? You can just go to Google Slides and watch this video. So let's do some practice problems. right? So let's take a look at question 6a. Again, feel free to pause the video if you want to try and solve this yourself. I'm just going to go ahead and underline everything that's actually important. And you have an impulse, right? You have an impulse of 15 Newton seconds. That's also the unit, right? Or you can just say kg times meters per second. Because again, J is F, essentially average or net times T. And so, well, what's force measured by newtons? What's time measured in seconds? So thus, the unit for J, the unit for impulse is Newton seconds. Or you could just put kg times meters per second. They will get you the same thing. Okay. All right. So now, well, now the question wants, well, what is the object's change in momentum? Right? What is the object's change in momentum? But as you learned from the previous slide, impulse's literal definition is your change in momentum. Thus, you're already given the answer. It's 15 Newton seconds. And you're done. So this question tests a student's ability to actually read the problem, right? So again, this is the answer. Let's move on. Again, feel free to pause the video. I'm just going to go ahead and answer this. So you have this mass, you have this, I'm just going to literally write m here. M traveling, this is your initial velocity. Brakes applied, brought to rest. So this is your final velocity is 0. And this is your time. And they want to know what was your total impulse J, right? So you're solving for J essentially. So J is equal to F net times T is equal to delta P, or it's essentially M delta V. We don't have a net force here. We have time, yes, we have time. Time is 5 seconds, but we don't have net force. So we are going to use this other formula here. I'm going to break it down. This breakdown is also shown on your notes. So I'm just going to go ahead and do it. So mass is that. And then delta V is essentially VF minus VI. So you guys can just plug it in yourself. Okay, so let's do this. Kg times final velocity is 0 minus V sub I. That's 25 meters per second. So you guys can solve this yourself. Okay, and then the work is shown on the slides. Let's do 6C. Kind of go through this. Again, feel free to pause the video. So I'm just going to go ahead and underline all these nodes. 1200 kilogram car is moving at 10 meters per second when a braking force of 3000 newtons is applied. It's actually incredibly important for you guys to notice the language here. A braking force. Think about it this way. The car is moving, let's say it's moving to the right, but then a braking force of 3000 newtons is applied. Well, think about the direction that force is applied in, right? If you're braking, well, then the force is applied in the opposite direction here. And so your net force here is actually negative 3000 newtons. And so what was your time? And then you bring it to rest. Sure, right there. Now, we don't have impulse. We don't know what J is. So really, we're not even going to entertain the fact that we are going to use J is equal to that because we don't have it. So we are going to use this formula instead. So now we know that delta P is equal to M delta V, and we know M delta V, I'm actually just going to break this all down, is equal to that. So negative 3000 newtons times T, mass is 1200 kg, final velocity is 0 minus 10 meters per second. And then I keep bringing this down. I resolve the right hand side, and then get that. Do this, and then get 4 seconds. Okay. Again, you can always just go back to the slides to review. Feel free to pause again if you want to do it yourself. This is mass. This is my initial velocity. This is my impulse. And it says here your impulse is westward, so your impulse is actually negative 2,000 Newton times seconds. What is the final velocity? V sub f of the car after the impulse has been applied. So what is V sub f? Now we can't use F net times C, right? Because again, if you look at this formula, we don't really know what F net is. We don't know what time is. So we really have to just use this. You just cut out the middle. And we can further break this down, right? Further break that down. So this is negative 2,000 Newton seconds. Mass is 1,000 kg. Final velocity is what we want to solve for, and then it was initially traveling there. You know, there's an easy way to do this without having to distribute this 1,000 into the parentheses. Just divide it by 1,000 on both sides. And now you're left with negative 2, right? So now you don't need to invest so much space. Well, you don't need that unit there. Then you do plus 20, and then you just get 18 meters per second. Okay? Feel free to pause. We come now to our final question. Again, feel free to pause. Stationary, which means the object was not moving. This is your mass. Average force, so this is your force. Accelerating to a speed of 44 meters per second, so that's final velocity. And what's the magnitude of your impulse? So what is J? Right, so we want to know what J is. Because again, you don't really have time here, right? We know that J is equal to F net times T is equal to delta P, but we don't have time, so we're just gonna cross out that middle part there, and we're just gonna do this. And so breaking this all down, mass is 0.05 kg, 44 minus 0. Oh, I'm not gonna do the math here. It's probably divided by 20. What, 2.2? Maybe. Let's see if I'm right. Yeah, it is 2.2. So 2.2 Newton seconds is or kg times meters per second. Okay, done.